Alright, what's up guys? This is Probability by Pitman, Chapter 3, Section 2, Problem number 16, Aces. A standard deck of 52 cards is shuffled and dealt. Let x1 be the number of cards appearing before the first ace, x2 the number of cards between the first and second ace, blah blah blah, so on. It can be shown that each of these random variables xi has the same distribution. I equals 1, 2, all the way up to 5. And you can assume this to be true. Right, part A. Write down a formula for P of xi equals k for 0 through 48. For k can be 0 through 48. So, where xi is just the number of cards, if I is equal to 1, it's the number of cards before the first ace. If I is equal to 2, it's the number between the first and second ace. You guys saw the what's up here. Okay. So, I think this is fairly simple. So we know that they all contain the same distribution, right? It can literally be even everywhere. So any card can exist everywhere by symmetry. So I think the best way to go about doing this is just saying P of xi is equal to k is equal to 48 order k. Wait, let's think about it. Because, for example, if k was equal to 2, we're saying there's two non-ace cards there. So 48 times 40. So yeah, okay, that makes sense. So 48 order k, 52 order k. And that should be our answer because no matter where the cards are put, um, they all have an equal chance of not being an ace. Um, like, actually, let's draw it out just to show. So, like, even if we're talking about this spot, which is x1, this spot, which is x2, x3, x4, x5, it really doesn't matter. For all we know, this is 0, this is 0, this is 0, and we're talking about x5, in which case, there are 48 non-ace cards remaining, and we can just do the probability like this. We don't necessarily know how many non-ace cards were played before, because so we'll just use the property of symmetry to know that each section has an equal probability of having aces and non-aces as any other section. Not that the probabilities of aces and non-aces are the same, that's not true, but each section will have the same probability of this occurring. And regardless of whether you think about it in terms of symmetry, they literally tell us that all of the variables xi have the same distribution. So that in itself tells us that this should work. I hope that wasn't too confusing. I don't think I explained that too well, but it's okay. I'm just doing this to study. Okay, part B. Show that e of xi is equal to 9.6. Okay, so once again, we have to use indicator variables. Yeah, okay. So show that e of xi is equal to 9.6. So let's let xi equal to I1 plus, figure out what our indicator is. Okay, so we'll do I1 all the way up to I48, where each of these indicator variables indicates whether one of the non-ace cards, the 48 cards we have that are not aces, are in that slot xi. So like in x1, let's say if it's like I1 is equal to 1 and I2 is equal to 2, and I1 is equal to like 1, or like the ace of hearts, and I2 is equal to the ace of diamonds, but then everything else is equal to 0, so that means this would be equal to 2. Xi would be equal to 2. So as a reminder, each indicator can be equal to 1, 0, and each indicator represents some non-ace card. Okay, cool. So now let's draw a little table. Actually, let's write it out in a good way. So where ij is whether the jth non-ace card is located in the slot xi. Okay, cool. So now let's draw our little table. So P of I, where that card, non-ace card, can either be located in that slot or it cannot be located in that slot. So just by symmetry once more, we know that each non-ace card has an equal chance of being in any of these slots. They have to be in one of the slots, but they have an equal chance of being any of the slots. So x1, x2, x3, x4, x5. So for xi, we're just talking about one of the slots. So let's just pretend we're talking about x1. So then our I1, our I2, all the way up to I48, each one has an equal chance of being in any slot. And let's say we're talking about x1, then we have so if there's 5 total slots, we have a 1/5 total chance of getting to that specific slot. So then the probability of our non-ace card being in slot xi is just equal to 1/5. And then obviously 0 will be 4/5, but that really doesn't matter for our calculations. So now that we know this, we can just do E of xi is equal to E of I1 plus dot 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 all the way up to I48. From there, we can use linearity of expectations. So it's also a good thing to write it out. I lost points once because I didn't write it and it was really dumb and I was kind of mad. So the linearity of expectation. And then remember, each of these is equal, so we might as well just write 48 e to the I1 since there's 48 of them and they're all equal. So we can just use e of I1 to represent all of them. And then remember, e of I1 is equal to 1/5 because 0 times 4/5 plus 1 times 1/5. If you use the definition of expectation, so 48 times 1/5. So our answer is 48 over 5. Julio. Alright, part C. Are x1 to x5 pairwise independent? They are not. Because if you think about it, so pairwise independent says that all the pairs, it doesn't matter what they are, it doesn't affect the results of the others. So x1, x2 will not affect the result of like x2, x3, for example. But think about it, like this value has to implicitly affect this value because guess what? The value of x2 that impacts this one, it's also going to impact this one. So whatever x1, x2 ends up being does impact what x2, x3 can be. And think about it, like if you have x1, x2, x2, x3, x3, x4, and then all the other possible combinations except for x4, x5, obviously all those things added up, all those things, what values you get, not added up, sorry, all the values you get in those ones will impact what's possible to get in x4, x5. Because if you maybe you got all 48 in all the other combinations, then this one has to be 0. These two have to be 0 if you got it in all the other pairs. That was kind of, it's a weird explanation, but I think it kind of made sense. All right, so we have to prove our answer. All right, I'll pause real quick. All right, I want to re-explain my answer for part C in a more concise way. So if you have like x1, x2 as a pair, and let's say they have 48 cards, that means we know x3, x4, x5 as a pair has to equal 0. So therefore x3, x4, x5 is dependent on x1, x2. Therefore, our variables cannot be pairwise independent. And I think that's adequate as a proof. I'm not entirely sure how you'd write it out, and my cursory Googling doesn't really show a way to write it out. There probably is a way, but it's okay. It's just for me to study. Okay. And then I just realized I made a grave mistake in part A. So I'll go ahead and redo the whole part A. I've done a formula for P of x equals K. Okay. So let's say K is equal to 0. So that, okay, actually let's write out the whole thing. So P of x equals K. So let's say K equals 0. Then that means we drew an ace immediately. K equals 1, we drew a non-ace. Then we drew a ace. K equals 2, we drew a non-ace, drew a non-ace, but then guess what? We drew an ace, and so on using this pattern. So while I had the right idea, I just completely forgot to account for the fact that, this can still happen where, wait, why did I write 1/4? Sorry, that's 4 out of 52. Sorry about that. Okay, so I just forgot to account for the fact that, um, even though you're drawing a bunch of non-aces, you have to count that right after drawing these non-aces, you will draw an ace. It's very important to do that because these segments represent things between aces. Whereas in the way I did it, it's just drawing non-aces, which doesn't really model our situation very well. So my bad. But from there, now that we understand this, our answer is pretty easy to figure out. It's still 48 order something, but it won't be k. It'll be k minus 1. Then our denominator will still be 52 order k, and then we'll multiply this by 4. So basically we did the exact same thing, except our kth value. Um, wait. Oh, I'm sorry. I still messed up. I messed up again. Okay, wait. Okay. So we have 48. We want to draw k from it. Then we have 52. However, we want to draw k plus 1 from it. And then we multiply by 4. Okay, so what you're seeing is 48 order k. So if k is equal to 2, then we have 48 times 47, as we can see here. Then, if we have k is equal to 2, so this is 52 order 3, so we have 52 times 51 times 50, then we multiply by the 4. So I wasn't thinking entirely clearly when I did this first part, but this is a better way to represent our model. Alright, cool. I made a bunch of mistakes. I'm sorry, but hopefully this video was somewhat helpful.